Good morning. Let me just first review a bit about what I talked about yesterday and what I promised you for today. This was concerning the Bloch and the Fermi varieties for periodic operators. And you'll remember that I had some discussion about Schrödinger and elliptic type operators in the continuum on graphs and on metric graphs. And then I promised that I would describe the Bloch transform. And that is the Fourier transform with respect to a shift group of transformations, of symmetries, and then show you how that allows you to decompose periodic operators so that you can find what we call the bands and gaps in the spectrum and how to do that. And what I would like to do today is actually show you a proof, or at least show you the outline of the proof that often people skip when learning this stuff, about how you do the decomposition of periodic operators by the Bloch transform, which is called Bloch's theorem in physics, or the Bloch-Bloch theorem in physics. All right. And here are some ideas from Kirill's talk that we thought we would try to keep up with. Let's see how well we can do with that. This is what I showed you yesterday, just to remind you. This is the overview, some Schrödinger and elliptic operators we talked about, what it means to be periodic. You have this fundamental domain that's repeated. And we had this shift group called Sj. And we were looking at eigenfunctions of the shift that were simultaneous eigenfunctions of the Schrödinger operator, right? And that's because the Schrödinger operator was commuting with the shift, which is the same thing as saying that the Schrödinger operator is periodic. It's just an algebraic way of saying that. And so therefore, we would like to decompose the Schrödinger operator on the eigenspaces of the shift operator. And remember that the eigenvalues of the shift are these Bloch multipliers. Eigenvalue just means you shift the function and it gets multiplied by a certain number. And there's a certain phase in there, which is a phase shift, and there could also be a scaling factor if this z is not on the unit circle. And then the exponential, if you write the Bloch multiplier as e to the ik times some kj, meaning in the jth direction, then that kj is the jth component of what we call the quasi-momentum. That's the phase shift. Okay, so these are the eigenvalues of the shifts. These are eigenvalues of the Schrödinger operator. And as I said, the goal for today is to show you how we first decompose functions with respect to the shift group. In other words, look at eigenfunctions of the shift group of operators. These U's, which are called pseudo-periodic or quasi-periodic functions. And then on each one of those spaces of quasi-periodic functions, that Schrödinger operator should be invariant because it commutes. And so we look for the eigenvalues of the Schrödinger operator on each one of those subspaces and thereby get simpler problems for the Schrödinger operator by decomposing it onto the subspaces of the shift. You see? And so for each one of those subspaces for the shift operator, we have this quasi-momentum. Then we find all the energies of the Schrödinger operator for that quasi-momentum. And so that's the physical meaning of this decomposition of the operator. And I'm going to show you how to do that. And this is through the Fourier transform. So the first part of the agenda is to show you how to take an arbitrary function f in L2 of the original space and decompose that into these momentum spaces, these eigenspaces of the shift. Then after we do that, the second part is to say, well, now I have a Schrödinger operator that commutes with that, with all the shifts. So therefore, the Schrödinger operator should be decomposed. What's the proof of that? How do you do the proof? And I want to show you an abstract proof that's actually written. I got this, so there's a very nice rendition of this stuff in Reed and Simon's 4 volumes. It's the very last volume at the end. It doesn't mean it's extra hard, but that's where it is, right? It's the end of the 4th volume. All right. And I gave you an example of graphene. And we did some Schrodinger operators. We talked about continuous Schrodinger operators in RD. We talked about the evolution that those Schrodinger operators give you in quantum mechanics. That's the time dynamics. And we talked about some discrete Schrodinger operators, including magnetic ones down here. And then a little bit about metric graphs where the Schrodinger operator actually, where the states actually live on the edges of the graph. And the Schrodinger operator looks like this with certain vertex conditions. So you can make up lots of different things. And they're fun. Now we start with the Floquet transform. The Floquet transform is a terminology that was attached to the Fourier transform with respect to a shift group because of its association with Floquet. It's also sometimes called the Gelfand transform. It depends exactly how you parse it, or the Z transform in engineering, because you use the letter Z, right? But it's the Fourier transform with respect to the shift group. I'll show you exactly what that means. And keep in mind that what you're looking for during this first part of my exposition is you're looking for me showing you how you can take an L2 function and decompose it into the eigenspaces of the shift, right, to the momentum spaces. So look for that. That's the point of this. All right, now I'm going to abstract everything. And the ideas that are going to be extracted are the following. In any of those three examples that I showed you already, you have an underlying spatial space, like RD, or the graph, or the discrete lattice. That's thought of as being space. And there's this translation group. And there's a certain way in which you measure space, and that is invariant under the translation, right? So we're going to abstract that idea, and I will start with a measure space, X. So this is just a space, X, a set, and B, this is the formal terminology for a space X. This is like the Rn or the Z, the graph or whatever the underlying space is. And then this means that we have a set of measurable sets. So this is how you do this formally, mathematically in analysis. And then there's some measure. In all of the examples I showed you, it's just the obvious measure. It's just the way that it's generated by just measuring open sets or open balls and extending that to what we call Borel sets or even beyond, finer than Borel sets. So I would be, in the examples I showed you, it's really Lebesgue measure. Now, there's something called an action. All right, so what you do is you take an element of ZD. Think of ZD as the translational symmetry group. ZD is just all integer D tuples. So you take a vector of integers and you think of those integers as a translation in D different directions. You see, it's discrete, so you can only go by integers. So that's why ZD is thought of as being a translational symmetry group. Translation. And this terminology means that you take the underlying space, like RD, and you apply an element, you take then an element of the shift group, and you put them together in this pair, and this corresponds to the shifting the point X by this N. And this is the terminology that it's really very convenient. It's a little confusing at first, but it looks like I'm taking a point X and I'm literally adding N to it. What this really means is I shift by whatever the shift vectors are. And you see the N here is N1, N2, N3. That's the N. So you have all these shift vectors. So this would actually mean, I'm going to show you, okay, look, this will be a little abstract for the first part, but then I'm going to show you these examples so you'll understand. So this just means the shift group is acting on the points of the underlying space. Since it's an additive group, we like to do plus N instead of N dot, because it feels better to keep the additive nature of it. So that's the notation for the shift group action. All right, now it's a free action. What does that mean? Essentially, it means that if I take any X in the space and I look at all the different shift vectors that I shift by, that's injective. So in other words, I start with one X, I do all the shifts, and I really get a copy of ZD. It's just a lattice. So I take one X, do all the shifts, and I get a lattice that looks exactly like the group ZD. So there's no overlap. So there are no two shifts that take me to the same point or back to where I started. There's no torsion. Sometimes they call it that. Okay, and that's free action. So every shift gives you a different point inside of this underlying space X. And I said here, in other words, orbits just look like ZD. An orbit is just all of the points you get starting at a certain point by doing all of the shifts. That's the orbit. It's not orbit like going in a circle. That's a little confusing with the English word orbit. The orbit doesn't come back. Okay, that's what it is. That's what free means. Now, what's important here is that the shifts preserve the measure. Now, I should have called it nu, not mu. So that's nu. Okay, the shifts will preserve the measure. Just means if I take all of the X's in the space and I shift them by this group action, the measure. I'm sorry. Yeah, it's an isometry. That's correct. And in particular, it's an isometry of function spaces L2, which I will get to. Yes, so it's an isometry of the underlying space. In other words, if for any measurable set, basically any set you can measure, if I shift that set by n, then it has the same size. It has the same measure, right? That's important here. And I'll show you why that's important. There's a fundamental domain, W, which consists of, it's a set containing one representative element for each orbit. Okay, because this is not transitive. Transitive action means that if I start at any point, I can shift to any other point. Okay, and it's important in the periodic problems that they're not always transitive. Otherwise, it would be things would be really quite simple. And I'll show you what this fundamental domain is just in a second. So think of the fundamental domain as representing all the orbits that you get by shifts. There's 1 point per orbit. Okay. Now, given that we have this set that contains 1 point per orbit, you can represent any elements of the whole underlying space. Think of RD, if you like, by taking an element of W, the fundamental domain, that's a representative of the orbit, and then shifting to X, because X is in a certain orbit. Take a representative of X, of the orbit of X, and then shift to X by some n. And so you can represent any point in the space by an element of the fundamental domain plus an integer shift. Okay, unique way. This is actually important in applications because there's a certain interpretation here. We think of the y often in this fundamental domain as being a local variable and the n as being a global variable. Let me show you what I mean by that in this example. Let's do example 2 here. Let's do example. This is, example 1, part 2. Let's do example 2. Where the underlying space is actually R2, and adding just the elementary vector in one direction just means shifting by V1. So this would be X, this would be X plus the vector 1, 0, because I just shifted in the V1 direction. This one would be X plus 0, 1, because I shifted in the V2 direction. This one would be X plus 1, 1, because I shifted in V1 and V2 directions. So you see what I mean by adding a vector formally means just adding a certain multiple of a certain combination of the V1 and the V2, which are the elementary shifts. So what do I mean by local and global variables? If I take any point right here, take a point right here, I can take a point that is that you can shift. I can shift this point back to a certain point in the fundamental domain. So this point has a certain orbit. You just look at all the different points that you can get by shifting that one by combinations of the V1 and the V2, and you get all these red points. One of those will land in this W set, which is a fundamental domain because it's determined in such a way that it contains 1 point, W contains 1 point from every orbit. You see? So if I take this one, the corresponding point to W would be here. And so you can see that if I take any X, I can go to its representative in W and then shift however many copies of V1 and V2 I need to get there. So this X is represented by this Y here plus a vector, which would be in this case 2, 1, because I took 2 steps in the V1 direction, 1 step in the V2 direction. Okay? And so do you see how the N is like a global variable because you don't see the microscopic structure. So if in homogenization, this W really becomes very, very, very small, then it genuinely is a microscopic variable. You see? And then the N is the macroscopic variable, and this macroscopic variable N, which is actually discrete, it becomes continuous as you step away, and it looks like a continuum. And that's what Peter and others will show you in homogenization theory in that course. All right. Here's another example of a periodic metric or discrete graph. This is a fundamental domain. So the blue stuff here, you can see the part that's blue there, that's the part that's repeated periodically. But you can't get from any one point in here to another point by shifting. It's not transitive. So that's your fundamental domain, all right? And so the microscopic variable is within W, the macroscopic variable is the shift. Okay. All right. Now let's look at the induced action on functions. So this, let's say that we have ZD again, acting freely on X, just like I explained, preserving a certain measure mu. Now let's take a function from X to Y. And this Y is typically the complex numbers or some other Hilbert space of states that you can identify at a point. Values of a function in some Y. Typically complex numbers. And these F's are like states. So these are functions. In quantum mechanics, states are functions of the underlying space or some transformation of that space. And so take a certain shift vector of this function. What you do to shift a function is what you do in kindergarten is you just apply it to the argument, right? You do X plus N, that gives you a new F just by shifting the function. Now in harmonic analysis, you're really supposed to put a minus sign here. And that has to do with making sure things work right if your group is not commutative. When it is commutative, then you might as well put a plus. And this is traditional for analysis to do it this way. And it's okay. So this N acting on the function F, by definition, is just shifting it. Shifting a function means shift the argument. Okay, so you apply the group action on the argument, and then you pull back the function. It's really pulling back the function by the group action, if you like to think about it that way. So when Y is a Hilbert space, this ZD becomes a unitary group of operators. That's what's important. That's why it's in blue. A unitary group of operators on L2 of X with values in H. So if this F is actually in the L2 space of functions on X with values in a Hilbert space, which could be just the complex numbers, then why is it a unitary? Why is this unitary? It's because when you shift a function and the measure is invariant under the shift, then the integral will be the same. Right? And so therefore, the L2 norm is preserved under shift, or any other integral norm, but particularly L2. So this is a unitary group of operators on L2. In the language of representation theory, you would say that you have a unitary representation of ZD on L2. And that's by shift. Now let's look at characters, weights, and Bloch modes, what all this is about. So the formal way to talk about the generalization of Fourier analysis with respect to group actions is something called a dual group. Dual group of ZD is the group of what we call characters. Now, if you want to relate this to linear algebra, think about taking a vector space, and then the dual of that vector space is all linear functionals on that vector space. In other words, functions from the vector space to the field R or C, let's say, that preserve the vector space properties. What we do here is now, in the context of just groups, rather than vector spaces, we take the group and we map it to some standard group, which is C star. C star is the complex numbers minus the origin. So it's the multiplicative group of the complex numbers. Okay. We use that group as the target space. So you look at all the characters, which is the dual group consists of all characters of ZD, which is homomorphisms. Homomorphisms means it just preserves the group structure. Homomorphisms from ZD to the standard group C star. Those are called characters, and the set of all characters is actually a group itself, and it's called a dual group. So a character phi from ZD to C star is actually determined by D different numbers. In other words, if I take an elementary vector from ZD, so E1 would just be 1 and then all zeros, etc. And E2 has the 1 here, E3 has the 1 there. So if I take an elementary vector from ZD, that homomorphism gives it a certain value, Zi. And if I know these D different numbers, that will completely determine the homomorphism, just like a linear functional is determined by its values on a basis, right? It's the same thing here. And so all of the characters are just determined by these things called Zi. Those will actually be the Floquet multipliers. So this is going to be, I think, very interesting for you in just a second, when we get to the raison d'être of characters. This is the reason for their existence. Okay. It's a little arrogant to say that maybe in general, but I think in this context, it is the reason for their existence. So let's see. Yeah, so therefore the dual is identified with this C star to the D power. Okay, so any homomorphism, any character is actually determined by D different numbers in C star. And so the dual of ZD is identified with C star to the D power, all the characters. I'm going to show you why we need these things called characters, homomorphisms, which is important, from the shift group to C star. Any function from the shift group to C star is already a function of the shift group. It's already a function. It's going to have certain properties. Okay, if it's being a homomorphism. I'll show you why that's important. Okay, now, so for any Z, this is repeating what I said here, more explicitly, for any Z in C star to the D power, there's an associated character, this thing called phi sub Z. That's a function from the group ZD to C star that takes a certain n here, a vector, to just Z to the n power. Z to the n power is a shorthand for saying I take Z1 to the n1 times Z2 to the n2, etc. Remember I told you that if I know phi of EI, then for each elementary vector, then I know the whole homomorphism by extending it, because the ZD is generated by these elementary vectors. Therefore, the homomorphism needs to be generated by the values at those elementary vectors in order to be a homomorphism. And this is how you do it. You see, if I send n to Z1 to the n1, Z2 to the n2, etc. Then now I have defined in a unique way a homomorphism from the whole group to C star, generated by its values at the elementary vectors. Okay. So these are the characters. And this thing here in representation theory is typically called the weight vector. And I'll show you why these, okay, so these things are called the weights or Floquet multipliers. Why do I suddenly bring in the word Floquet multiplier? I'm going to show you in a second. Because Floquet multipliers are supposed to be eigenvalues of a shift. So why are these weights actually eigenvalues of a shift? It's because it's a homomorphism. I'm going to show you that. And the unitary characters are exactly those where all of the z's have modulus 1. And we call those the torus, the d-dimensional torus. it's all of the z's inside of c star to the d power, where the moduli of all those z's are actually equal to 1. And so you can call zj e to the I kj, where the kj is real. All right. This is a compact torus. In algebraic geometry, they call this here the torus, which for us is the non-compact torus. And then they call this the compact torus, which in topology is usually the torus. They're topologically the same. One's contractible to the other. So they just call this a non-compact torus. We like to call this the torus. All right, what's the reason for existence of characters? This is really important in Fourier analysis. This is pervasive in all Fourier analysis, and then goes into representation theory when things become non-commutative. Okay, so the characters, the homomorphisms from the group to C star are eigenfunctions of the ZD action on itself, basically on functions from Z. Suppose you just have one orbit, then you can just identify the X space with ZD itself. So I can take functions on Z from ZD to the complex, let's say. All right, well, characters are functions from ZD to the complex numbers, not including 0, but they do go to the complex numbers. Now look, I'm going to take the action of n on a character. Remember that the character phi z takes n to z to the n. Okay, it's a homomorphism. So when I act by shift on a homomorphism, what happens? I take the homomorphism and I shift by n. The homomorphism itself acts on integers, and then I shift the integer by n. Being a homomorphism, it pulls out the value of the character, which is z to the n. That simple. It's like so simple, it's deceptive. So, but this is the reason for existence of characters, as far as I'm concerned. If I act, so again, I'm going to repeat this. I take a character which is a function on ZD, but it's a special function. So special that if I act by n, it multiplies by z to the n. So it's an eigenfunction of the shift because it's a homomorphism. Homomorphisms are eigenfunctions of the shift. That's what homomorphism even means. Right? So this is very nice. It's one reason I'm really harping on this is that no one ever told me this. And one day I realized it and I was like, wow, life is so much easier after I saw it. I don't know, people just don't say it this way. But this is how things work. The weights are the eigenvalues. You see now? I just want to make sure we don't. Apply n to this function. Say it's multiplying by z to the n. Therefore, it's an eigenfunction of this action with eigenvalue z to the n. Of course, the eigenvalue depends on the n. The eigenvalue itself is a homomorphism. It is the character. So, yeah. And the weights are the eigenvalues of the elementary actions. So now these what I've showed you so far is how the characters themselves are eigenfunctions of within the space of functions on ZD, the group itself. But now when more generally, when we have a free group action, we have many copies of ZD, one for every point in the fundamental domain. And so you can think of putting a character on every one of those those orbits. Okay, and that's how we can extend these eigenfunctions to functions, more generally functions on X with values in C, because the X just consists of a bunch of orbits anyway, right? And so what I do is I look at this decomposition into microscopic and macroscopic variables. This Y is an element of the fundamental domain. And then I can shift that around by n to get an orbit, which looks like ZD. You see, if I fix the Y, I can look at all points in ZD, all shifts, and I get all these different X's. And that just looks like ZD. And so I can take a function, f of X, and I can write this X in terms of an element of the fundamental domain and an element of the shift group. And if I start off, see, what I want to do is start off by defining the values of f on just a fundamental domain. On one point of each orbit, I define what I want the f to be. Then I'm going to shift, I'm going to define f at every other point by shifting that y by n and multiplying by the character. So all you're doing is you're putting that homomorphism at every one of the orbits and scaling it by a particular value. And so what you get is a function so that when I shift by n, I multiply by z to the n. This is how you create from characters all pseudoperiodic functions on the underlying space. You just determine a value for every point in the fundamental domain, and then you continue it by multiplying by the Bloch multiplier. Does that make sense? I know people who are watching by Zoom won't be able to see this, but I just want to make sure it's clear, and it might be totally clear right now, and I might be wasting time here, but I just want to make sure. If I have periodic structure, and this is the fundamental domain here, I take any point in W and assign a particular value, f of that y. Assign the value to every point in W. So I have a function in W. And now I take that function to get the values over here, I just multiply by that particular Bloch multiplier, C1. So I take the f at y, and I multiply by Z1. That's the new function here. It just gets multiplied by the eigenvalue of the shift. And now to get it over here, it's going to be Z1 squared f of y. This is the f of this x, where x is equal to y plus 0. Yes.
Most of them, it doesn't look this green won't look well.
You are right. I agree. I'm not being a good teacher. I agree. And I probably should write over it. So. I have a function here defined in a fundamental domain, and that is enough for a particular character set of Bloch multipliers to determine a pseudoperiodic function. Let's take the values here, and then I multiply by Z1 to get the values here. I multiply by Z1 again to get the multiple values here. I multiply by Z2 to get the values here. And so I create this function where the shift just corresponds to multiplying by some power of Z1 and some power of Z2, depending on how many shifts I did in the two different directions. And those are pseudoperiodic functions. That's what I'm saying here. Okay. And so restricted to any particular orbit, it's just a character, it's a homomorphism. Okay. Of the group action. Okay. So now we can look at the eigenspace. So I've just created these functions that are eigenfunctions of the shift with the different Bloch multipliers corresponding to each one of the characters. And so I have an eigenspace. So I just constructed all functions for any particular character. And so this eigenspace is just now the set of all functions from x to c, so that when I shift it, under the shift action, you multiply by that particular character z to the n. So now we think of characters as being more generalized eigenvalues that actually depend on how many shifts I did. Okay, so this is my these are the eigenspaces of the group action, the shift action by ZD. That's what these are. These are the spaces. So I told you that you're supposed to look forward for me showing you how to decompose functions on these eigenspaces. These are the eigenspaces now, you see? I just showed you for the shift group. That's what they are. Now I have something that commutes with the shift group, so that my operator better be invariant on these eigenspaces. See? That's on pseudoperiodic operator functions. So these are what's called the Bloch modes, or quasi-periodic pseudoperiodic functions. And if, so now let's suppose that, let's look at what happens when Z is actually in the compact torus. In other words, all the full K multipliers have modulus 1. Then I can just write them as e to the I k 1 up to kn, and these are the quasi-momenta. And so, I'm sorry? Yeah. So again, that is correct. So these are actually rotations, and which actually corresponds to, oh, thank you. So these are rotations, and they actually correspond to a phase shift. That's right. So the multiplication by a unitary number is a phase shift. Yeah, and it's a rotation if you think about it on the unit circle. Yeah, and the amount of the rotation is the quasi-momentum in that direction. And so the shift now corresponds to multiplying by e to the I k n, and that's this. Look at this. This is just a plane wave. So now we have the generalization of Kirill's plane waves from yesterday for a structure that is not homogeneous, but is kind of discretely homogeneous, right? So look, this is actually a plane wave in the macroscopic variable n, which is discrete. And this is the dependence on the fine structure. So I could just put a y here, because I could just put y plus n, where the y is in a fundamental domain. That's the microscopic variable. This is the macroscopic variable. In homogenization, the period, the W, the fundamental domain, becomes so small that you can't see it, basically. And so the n, the integer lattice, becomes macroscopic, and it becomes a continuum. And you try to find effective material parameters with respect to that macroscopic variable that are induced by what happens on the microscopic one. Yeah. Anyway, so now we have these things called Bloch waves. That's what this is. That's a Bloch wave with a quasi-momentum or wave vector equal to this k. Now, it's convenient sometimes when you can to try to find a distinguished element of EZ that you can use. And for what we call a gauge transformation. And what you do is you can take any pseudoperiodic function, pseudoperiodic with flow K multiplier Z, so inside of EZ. So if this F is inside of EZ, I would like to be able to factor out a kind of distinguished pseudoperiodic function, whichever it may be, and then what's left will be periodic. Okay, so I can use this periodic version. It's like the periodic part of this pseudoperiodic function. You see the F tilde would be in E1. E1 meaning you shift by in any direction, and it doesn't change. So the eigenvalues are all 1. See, so that's a periodic part times this distinguished pseudoperiodic function. Let me show you exactly what I mean by this. Then you can call the F tilde the periodic factor. So these are two examples from above. In the case of example 2, where we're in RD, you can just take the different, you can take an x, what I'm writing here is just that you can take an exponential function inside of the fundamental domain that will interpolate through all of the different orbits, so that I can actually, so that I have the pseudoperiodic function that's genuinely an exponential. Now, if I have just take the integer lattice, if I have an exponential on the integer lattice, I can interpolate that into RD just by a formula. And you can take that to be your kind of distinguished pseudoperiodic function. But you can't just necessarily do this on any graph. Or any other situation where you can't just naturally extend the exponential into the fundamental domain. All right, that's not so important. Okay, now the flow K transform. Here's the important part. I've showed you that you have eigenspaces for the shift, and I've showed you exactly what those eigenspaces are and how you can construct those eigenspaces for the shift, for all the different eigenvalues for the shift, which correspond to these characters. All right. Now, I want to show you how to take any function from x to y. Y can be your favorite Hilbert space, just the complex numbers. And I want to show you how to find how to decompose f into those different eigenspaces. And then we're going to go to our Schrödinger operator and decompose it onto those eigenspaces. But first, we need to know how to do the decomposition in a practical way. It's this thing called the Bloch transform, which is essentially the Fourier transform with respect to the shift. Now look what I have here. This f hat, which is the Bloch transform, has this new variable z, which is the characters. This is how Fourier analysis works. The new variable is basically all the exponentials. And typically, you just use the Bloch, you use the k rather than the z. I'm using the z because that's the character. And I'm also going to take a point in the orbit. This could be, you could take it to be y in a fundamental domain, but you can start at any point in an orbit, and then you're going to translate around to that full orbit. So you take f evaluated at every point in that orbit, and you multiply by the character. Okay, and this looks like a kind of inner product, and it is a generalization of an inner product where you're projecting onto a certain eigenspace. So this is the way in which it works. So if you write this down, even symbolically, it turns out that, again, this is the reason for this particular formula, that if you take this result of doing this formula, it turns out that this is actually an eigenfunction of the shift. So if I shift in x, I actually pull out z to the n by this formula. This is the formula that does it. You can verify this in your head, or you can do it on a piece of paper. You've probably already done it in a Fourier analysis course. But this formula, which is the Bloch transform that takes an f to an f hat, which f was a function of x, now it's a function of x and z. It has the property that when you shift in the x variable, you pull out z to the n. Okay, so you actually, in a way, projecting onto eigenspaces. All right. See, the f hat of z as a function of x is in EZ for fixed z. It's in that eigenspace of the shift. And now here, this is Fourier inversion. Why does that formula, which gives you these pseudoperiodic functions, why does it correspond to a decomposition of f onto the eigenspace? It's because you can recover f by the Fourier inversion formula, which says that if I integrate these f hats over the unitary characters, just over the torus, then I recover the f, the compact torus. Now I've defined this f hat for any z, and you know, a good student would ask me, well, how do you know this even converges, right? Well, you don't. A very nice thing about this is that symbolically it's fine. This is a Laurent series with coefficients that are shifts of f. You can't argue with that. But now what's interesting is that whenever this does converge on the torus, then you can reconstruct the f by integrating over the torus, the actual function of z for that particular x. You're integrating with respect to z. This is just the usual volume on the torus, but you have to divide by 2 pi to the d. So I'm just going to call it tilde, so I don't have to write 2 pi to the d every time. Integrate over the torus, you recover the f. That's the inverse Fourier transform. So a discrete infinite group Fourier transform to a compact continuous group, and vice versa. And you can write this as just integrating over the quasi-momenta k, 0 to 2 pi d times the Fourier transform. And then you can think of the c as e to the ik, and you're back to more familiar ground. See? Now, here's a more usual way that people write the Fourier transform. If I take out this distinguished pseudoperiodic function, and so that I can write the pseudoperiodic f as a periodic part times this one, then this becomes the Fourier kernel. That's exactly what it is. Okay, and then the rest is periodic. So what's interesting here is that when you do the Bloch transform from this point of view, you directly get a function that is already pseudoperiodic, so you don't have to multiply by a kernel. But if you take out the kernel, then the usual Fourier inversion formula has this function. Since it's periodic, it's actually thought of as being defined on a fundamental domain, the macroscopic variable. And then this is the Fourier kernel. So Yeah, there are a lot of nice ideas here. Every time I think about it, I think of something new that should have been obvious from the beginning. But so here's the unitarity of the Fourier transform. If I call the Fourier transform U, it turns out that this is an L2 isometric isomorphism from L2 of X to L2 of the torus, but with values in L2 of the fundamental domain. You see what I mean? The Fourier transform is done with respect to the shift action. You see the shift, if I take a point in X and I look at the shift action, I only access this orbit, which is a discrete subset. And so the Fourier transform is only really resolving at that. It doesn't resolve the fundamental domain because the shift action is not transitive on the fundamental domain. You see? And so the Fourier transform leaves unresolved this part that's defined on the fundamental domain. That's the way to think about this. So in other words, you're doing Fourier transform on the macroscopic variable, and you're not touching the microscopic variable. So it remains here. You see? And so the way I like to think about this, and I didn't really, oh yeah, so here, I wrote it down. Think of L2 of X. So this is the right way to think about it. Think of L2 of X. Right here, the original space is B. L2 of ZD with values in L2 of fundamental domain. See, so you can say, well, at every point in this lattice, I have a function, and that function is a function on this fundamental domain. So it's like it's as if the lattice were expanded into a fundamental domain at every point. So like you can take this, put it up here, so you have all these little fundamental domains at every point. And so at every point, they have a function of its corresponding fundamental domain. Does that make sense? So you can think of L2 of the original space that's divided as L2 of ZD with values in that copy of the fundamental domain. Now, from this point of view, just before you transfer with respect to ZD, the values are in L2 of W, so the values of course stay there. But before you transfer the ZD to the torus, by the usual Fourier transform, discrete Fourier transform. So that's a very nice way to think about it. Is that okay? All right. And so some nice notations for this. This is actually the tensor product of L2 of T of the torus with L2 of the fundamental domain. And a very nice way to write this is what we call a direct integral of L2 spaces over the torus. So for every element of the torus, you have a copy of L2 of the fundamental domain because the group action didn't resolve the fundamental domain because it wasn't transitive on that part. So that part's unresolved. That gets resolved by the Schrödinger operator. So let's show how that happens. You can also write this in terms of the periodic part. Now let's go to periodic operators, or more generally, operators that are decomposable with respect to a certain group action. In other words, they commute with that group action. So an operator A in L2 is deperiodic if it commutes with the translational symmetry group. And I mentioned this last time. In other words, if I first translate F, that's what this means. Remember, this is the notation for translating the argument. And then I apply A, that's the same as first applying A and then translating. It's simply saying the coefficients of the Schrödinger operator are periodic. The Bloch theorem says that A is decomposed, or Bloch, this is not Bloch, this is actually Bloch, diagonalized by the Bloch transform. In other words, there are these operators A hat of Z in L2 of W such that if I apply A to a function and then take the Fourier transform at Z, that's the same as taking the Fourier transform of the F and applying this operator to L2 of W. You see, because F hat of Z has values in L2 of W, the part that wasn't resolved. And so this operator now, so the A which was acting on functions on all of X now is acting on functions on just a fundamental domain. Okay, but in different function spaces for the different pseudoperiodic, the different pseudoperiodicities, the different Bloch multipliers. So another way to write this is that if I apply A to F, this function of X is actually an integral of the components in the different Bloch, for the different Bloch multipliers, the different momenta, where I have to apply this smaller type of operator, sort of more restricted operator, to the F hat. Now, decomposable operators are treated in Reed and Simon, their series on mathematical physics, analysis of mathematical physics from the 80s, in volume 4. And they talk about direct integrals of identical Hilbert spaces, which is what we have, over some measure space. And so they talk about a Hilbert space as being the direct integral of smaller Hilbert spaces over some measure space. So you think about this as being the torus, and this as being L2 of a fundamental domain. Now we abstract it to an arbitrary Hilbert space here and some measure space. And this is just a nice notation for saying I have L2 of a certain measure space like the torus with values in some Hilbert space. In our case, the Hilbert space is L2 of the fundamental domain. But now you abstract this to a measure space and some Hilbert space, and you get this bigger Hilbert space. This is another nice way to think about it. It's just L2 with values in C tensored with the Hilbert space. And so any H and any F, any function or any element of this bigger Hilbert space is of this form. You just take an element of the smaller Hilbert space as a function of M, and it's measurable in an appropriate weak sense. Okay, so you just, F is decomposed on this measure space into this smaller Hilbert space. Okay, so it's a decomposition in that way. Fourier transform does that for us with respect to the group action. It already does this for us. Now, we talk about what we mean by decomposable operators. Decomposable operators with respect to this decomposition of a larger Hilbert space by a smaller one are operators that are defined by individual operators on the fibers on each point in this measure space. In other words, an operator is decomposable by this decomposition of functions if the operator acting on every function in the larger Hilbert space is obtained by integrating over individual operators for every point in the measure space acting on the fibers of that function. In other words, I decompose F into these FMs. And if the operator is also decomposed by individual operators for every M acting on those components, then you say it's decomposed by this direct integral. And so it's really diagonalized, but kind of block diagonalized. It's local. This A acts on each M separately. At each point in the measure space, it acts by a separate operator. They're not coupled. So this is decoupling into all the different M's. Right? And that's what the Fourier transform is going to do. We have to prove it. So the fundamental theorem for decomposable operators, and it really is the fundamental theorem, you see, says that an operator in a decomposed space in this way is decomposable. In other words, it can be written as individual operators on the fibers if and only if A commutes with all of the decomposable operators of this form. What this says is that this is just a multiplication operated by a scalar. This is the identity operator, and this is just a scalar function. So if A commutes with all operators that just act by multiplication, scalar multiplication on the decomposed F, then so that's equivalent to A being decomposable, commuting with these special decomposable operators that are scalar multiplication. Okay, that's the fundamental theorem on decomposable operators. And you can extend this to unbounded operators, which are Schrödinger operators are, by looking at the resolvent. There's a proof of this, but I guess I'm not going to show you the proof, but it is in the notes. Oh, actually, no, I have a proof of the decomposition theorem down here. But let's suppose that I skip that. And let's say that I use the decomposition theorem to prove the Bloch theorem. So in other words, I apply it specifically to periodic operators. In other words, Schrödinger operators that commute with the shift, discrete shift group, periodic Schrödinger operators. Let's do that. So suppose that my Schrödinger operator commutes with the ZD action. That means it's periodic. The Fourier transform is unitary. We already know that. I already showed you that. And the tilde means you go to the periodic part. Now, let's say that we conjugate the A to the Fourier transform. So we look at how the A acts under the Fourier transform. So it means start in the Fourier variable, go back to the X, apply the A, and come back to the Fourier transform. So since the A commutes with the ZD action in the Fourier variable, the A tilde will commute with these. But how does ZD act under the Fourier transform? Just by multiplication by Z to the N. You see, these are eigenspaces for the shift. So the shift acts by now multiplication by Z to the N. And these, you see these operators, which correspond. So if I take a shift by N and I look at how that acts under the Fourier transform, it just is multiplication by Z to the N. Because the Fourier transform takes you to eigenspaces of the shift. And these are the eigenvalues. And these are just multiplication operators on the fibers, multiplying by constants. And so since the A commutes with the N, the transformed A commutes with all of these multiplication operators by Z to the N. And on the torus, this is just multiplying by E to the IKN. And we know that E to the IKN on the torus are complete in L2. Okay, and so it turns out then that we have that this operator A in the Fourier variable actually commutes with all multiplication operators by scalars. And therefore, by the theorem, we know that A can actually be decomposed by the Fourier transform. Okay, so by completeness of these on the torus, A tilde commutes with all scalar multipliers of this form. And by the fundamental theorem, the A is decomposed. Now, the A is just the original A in the Fourier transform. It actually can be written as a direct integral of operators. In other words, we have now obtained that our periodic operator can be decomposed onto the eigenspaces of the shift, just because it commutes with all the shifts. You know, when you write these notes, it feels like, oh yeah, this is simple. It's just because, you know, you see it in your head in a certain way. And when you explain it, you think, I wonder if I'm saying everything I'm supposed to say. So I hope I made this clear. Now let's look at some of the consequences very quickly, and then this will wrap up for today. I was supposed to get through part 4, and part 4 is just, it's really short because I forgot to write a part 4. I don't know how that happened. So let's look at decomposition of the spectrum. So now we know that our Schrödinger operator can be decomposed into these operators acting on each one of the eigenspaces of the shift, these spaces of Floquet modes. And there's a fundamental theorem involving spectra of decomposable operators. And one of those, the most elementary one, says that the spectrum of the original operator is the union of the spectra of all of the components of that operator acting on these different components of pseudo-periodic functions. And so for a periodic operator A, we find that its spectrum, A being periodic, means that its spectrum is the union of the spectra of all of these operators of the projection of the Schrödinger operator on these quasi-periodic spaces. So we can just look at A restricted to these quasi-periodic spaces and get the full spectrum of A by taking the union over all of those, over the whole torus. And I'm going to show you the consequences of this starting tomorrow. And of course, the main consequence is that you get these spectral bands. But since this, my lectures are supposed to be about the Fermi and the Bloch varieties, let's come back to that. In the example that I showed you above, I remember I showed you the example of graphene, and I showed you how we take the operator and assume that it's acting on pseudo-periodic functions, and then we get a condition for the A to have an eigenvalue on that space, and then we found that we have to take the determinant of a certain matrix, and we got a function. And this is what we did. We said, basically, that if I look at A on a particular momentum space, and I take the spectrum of that, E will be in the spectrum of A on that momentum space, if and only if a certain function was equal to 0. That was the determinant of a certain matrix. And this typically happens. Now, this can be a kind of a difficult object to get your hands on if you're looking at determinant of something that's not a finite matrix. But still, there's this function that's called a dispersion function that you can get out of this. And then you say, well, you have an energy for that momentum if and only if this is equal to 0. So this is encoding for every K on the torus, what's the spectrum of the decomposition of A at that particular quasi-momentum. And then now the task in application would be to take your periodic function, apply it to pseudo-periodic functions, and try to, which then gives you I'm going to take one more minute, if that's okay. I want to describe something here. When you do the decomposition of a periodic Schrödinger operator with respect to the Fourier transform, what you get is essentially that Schrödinger operator now projected or applied to pseudo-periodic functions. So pseudo-periodic functions are defined by the values on a fundamental domain. They're defined by the functions and the values on the fundamental domain. And their values on the two different sides are mediated by the Z1. In other words, the value over here is Z1 times the value there. The value here is Z1 times the value there. And you have to be a bit careful about also applying that to the derivatives depending on what space you're in or how many derivatives your operator has, such as a Schrödinger operator. But you can get all this stuff right. It's a little technical, it goes into subtle spaces. You get the domains right when you have a value operator. But what you do, and now this is going to lead back to Friedrich's talk yesterday, he was looking at bounded obstacles with certain boundary conditions, and you have an operator in here, and you have a certain spectrum. Now, what we're going to have is this is our object, and we have certain boundary conditions. When Z is equal to e to the I k, then it actually turns out to be self-adjoint boundary conditions, and you get real eigenvalues. The bounded domain, you get real eigenvalues. And so for every K, you get certain eigenvalues, and those eigenvalues change as a function of K, and you get these bands of spectrum that don't look like that. You get these bands of spectrum. I'm going to start with that next time. All right, thanks for allowing me to go a couple minutes.